Okay, troops, last wee bit about this circular motion or equations of motion for things that are turning in a circle is acceleration, angular acceleration. If I turn this record on, got a wee Beatles record on, watch. Okay, it has to, wait a minute, it has to start from rest and then reach its normal angular velocity in a very short period of time. In other words, it has to accelerate in a circle. That acceleration is called the angular acceleration. And for a turntable like this, that's a very, very, very high angular acceleration. Watch. Because if it wasn't a high angular acceleration, if it took its time to speed up, then it would go like this. Don't want that. You want it to be really, really quick, so it goes from rest to an angular velocity in a very, very short period of time. We've heard of this before, have we not? Wait till I put this here. It's got an initial angular velocity and it's got a final angular velocity, and it takes a time to do that. So, angular velocity, what symbol were we using? We use an omega. Final angular velocity, what are we going to use for that? Remember what we did at National 5 and higher? We used a U and a V. U for starting speed, V for final speed. Well, for circular motion, we use an omega for the final angular velocity. And we also use an omega for the initial angular velocity, but you put a wee zero in front of it. In fact, you call it omega naught. Omega naught is how you pronounce it, but it's an omega with a wee zero in front of it. Now, I bet you can guess the equation that we're going to use. What was it at higher? Let's put it up here. At higher, if we wanted the acceleration, it was A equals V minus U over T. That's the higher equation. Guess what we use in advanced higher for angular acceleration? Okay, let's think about the right hand side of the equation first. What's it going to be? It's going to be omega, the final angular velocity, minus omega naught, the starting angular velocity, divided by the time. It's exactly the same equation as A equals V minus U over T, but it's with angular quantities in it. And the symbol that we use for angular acceleration is an alpha symbol. So it's like A equals V minus U over T, but it's all angular quantities. Angular acceleration equals the final angular velocity minus the starting angular velocity divided by the time. Now, if this was 0, and this angular velocity that we want here, let's just say that that was 4.7. Let's do a wee example here. Guess what that's measured in? This is measured in radians per second. This is measured in radians per second. This is measured in seconds. What did we do at higher? This was meters per second, this was meters per second, this was seconds. What was acceleration measured in? Meters per second squared. Because it's meters per second divided by seconds. What will this be? Radians per second divided by seconds is radians per second squared. Now, wee example there. In my record here, we started off with an angular velocity of 0. We want it to accelerate up to 4.7 radians per second. Now, very expensive turntables will do that in a fraction of a second. In fact, this one has to do it in 2/10 of a second. So what would the angular velocity of the angular acceleration, of the turntable be? Well, alpha equals omega minus omega naught over T equals, put the numbers in, same as higher, 4.7 minus 0 over 0.2, and if my arithmetic is correct, 23.5. 23.5 radians per second squared. Angular acceleration is the rate of change of angular velocity. Now, let's go back. See, this record was playing. See, it's playing and I turn it off. It's got an angular deceleration. It takes 12 seconds to stop. I wonder if we could work out its angular deceleration. I'm back. Okay, let's work out its angular deceleration. So this time, its final angular velocity was 0. It started off, it was going at 4.7, and this time it took 12 seconds to slow down and stop. What's the angular deceleration going to be? Well, it's going to be a negative number, because it's 0 minus 4.7 divided by 12 is 0.4. 0.39. Let's go 0.4 radians per second squared. What have I forgotten? A minus sign. So, if it's a small number, then it's taking a long time to decelerate. And we want a really, really high acceleration here so that it starts instantly. Now, that's an equation of motion that looks very like A equals V minus U over T. I wonder if there are others of equations of motion that look like the ones that we met in higher. I'll see you in a bit. I'm back. Okay, so we have an equation for angular acceleration which looks very similar to the equation we had for linear acceleration at higher. Angular acceleration is the final angular velocity minus the initial angular velocity over the time. If we rearrange that, we get an equation that looks very like V equals U plus AT. Final equals initial plus angular acceleration times time. If that's the case, surely we must have an equation that looks a wee bit like S equals UT plus a half AT squared. What would that's the linear one, that's the straight line equation. What's the angular one going to look like? Well, what's our angular equivalent of displacement? It's angular displacement, symbol theta. So theta equals initial velocity, well, initial angular velocity is omega naught, plus a half acceleration, angular acceleration, times t squared. And there is our equation of motion, number 2, for rotational or angular motion. There's a third one though, wasn't there? Remember, v squared equals u squared plus 2as. What's that? That's the linear one. What's our angular one going to look like? Then, well, v final, that's omega squared, equals initial, that's omega naught squared, plus 2 acceleration, angular acceleration is an alpha, displacement theta. That is our rotational or angular equation of motion. And there's the 3 of them. They look similar. That's number 1. That's number 2. That's number 3. And just the same as you did at higher, when you used those 3 equations of motion to solve any equations of motion question, you can do the same at advanced higher, but for circular motion. We go back to this previous one that we had. If this record starts here with an angular velocity, ends up some time later with a final angular velocity of 4.7 radians per second, then what would its angular displacement be? Let's have a wee think about that. Here's the question. If, I'll just very quickly draw a wee circle here. If our initial angular velocity is 0, our final angular velocity is 4.7, the time that it took to reach that angular velocity was 0.2 seconds. That's radians per second, by the way. Then, what angle would it turn through? What would its angular displacement be? Which equation of motion am I going to use if I want to work out what angle it turns through before it reaches its maximum speed? Well, it would be this one, because we know what omega naught is, we know what t is, we know what alpha is, because we've just worked it out on the last sheet. Or if we wanted to, we could use this one, because we know what omega is, omega naught is. Which one will we use? Let's go with this one. Okay, I better add in my alpha from the previous page. It was 23.5 radians per second squared. So, this is like a 2-VAS question. Remember with 2-VAS at higher? Well, it's the same 5 quantities, but it's their angular equivalence. So, we're going to use s equals ut plus half at squared, but it's theta equals omega naught t plus a half alpha t squared. Sub in, well, omega naught was 0 because it started at 0, so that's a half times 23.5 times 0.2 squared, get my point in there, is, so what angle does that record turn through before it is travelling at its maximum speed? 0.5 times 23.5 times 0.2 squared is 0.47, round it, 0.5 radians, half a radian. Remember, a radian was about 57 degrees, so half of 57 degrees, 57.3 to be exact, divided by 2 is, it's about 29 degrees. Let's show you that on a record. So that record needs about 29 degrees to start and reach its maximum speed. So if I bring that back, it means it is starting. That's all it needs. Ready? There you go then.